Hello everybody and welcome to the first trig precalc video. A couple of notes here. I'm not going to pause when you should be working because you have a pause button as this is on YouTube. So if you need to do some work, pause that video and do the work. Like here, the do now. I'm not going to stop for 5 minutes while you do it. Pause the video. Here are the answers. Something to note here, this matrix right here, that actually has a name to it, and that's kind of like one of the things that we're talking about today. You can actually see that this one's pretty similar to it. So yeah, coming up with that name here in just 1 minute. So again, there you go for the answers. Here's the assignment that was assigned during the last lesson. You can find a link to the PDF of my answers on my website. So here we go. Today we are talking about section 7.6, the inverse of a square matrix. So back to those matrices that I identified on the do now, those actually have a name. They're called the identity matrices. They have different orders. Pause here for a second. The n by n matrix that consists of ones along its main diagonal and zeros elsewhere is called the identity matrix of order n, and it's denoted by right here. It is a square matrix, so it is the same height as width. And you can see I sub n. N just means the height and width of it. So you can actually have I2 is equal to 1, 0, 0, 1. I3 is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. Done. A couple other things here. Note that the identity matrix is square. If the order is understood to be n, you can just write I sub n as I. Pause the video if you need to write this down. Because I'm going to proceed and show you what the identity matrix actually does. We saw it on the do now when you multiplied by the 3 by 3 identity matrix. Nothing actually happened to the matrix. That actually works for any size identity matrix. So like looking at, let's just say we multiply the matrix 2, 3, 1, negative 7, 5, 0 by an identity matrix that can be multiplied by it. In this case, since this matrix is 2 by 3, I'm going to have to multiply by a 3 by 3 identity matrix. So just copying from up here, I can see that would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And I can see when I multiply the row by the column, I've got 2 times 1 plus 3 times 0, well that's 0, plus 1 times 0. So the first entry in the first row of this new matrix is going to be 2. If I go to the second row here, second row by first column, negative 7 times 1, well that's just negative 7 plus 0 plus 0. Hey, cool, first column's the same. Now I go to the second column. 0 plus 3 times 1 plus 0. 0 plus 5 times 1 plus 0. Last column. 0 plus 0 plus 1 times 1. 1. 0 times 0 plus 0 times 1. So you can actually see the matrix you start with. If you multiply by the identity matrix, you will end with the same exact matrix. Pretty cool, huh? Oh, I guess, yeah, just did that. Yeah, you can see actually it comes out to be the exact same thing again. Now for the definition of inverse matrices. So if A is an n by n matrix, and let I sub n be the n by n identity matrix, if there exists a matrix A inverse such that A times A inverse equals I sub n equals A inverse times A, then A inverse is called the inverse of A. The symbol A inverse, as you've heard me say repeatedly, is read as A inverse. A couple things to note here. In order for a matrix to be invertible, or what we call non-singular, those vocab words are going to come up later, so don't worry too much about them. But again, in order for a matrix to be invertible or non-singular, it has to be a square matrix, and the matrix times its inverse and the inverse times the matrix have to both be the identity matrix. So looking down here, I actually have an example of two inverse matrices. And just to confirm, because on your assignment for this section, you're going to have to confirm that two matrices are inverses of each other, you have to multiply the matrices together. So looking here, I've got negative 2 times 4, I believe that's 8. 2 times 9 halves, that would be 9. So I've got negative 8 plus 9. Second row by first column, negative 9 times 4, that is negative 36. Plus 9 halves times 8, well, half of 8 is 4 times 9, gives me 36. If you don't believe me, you can check that on a calculator or whatever you kids do these days. Negative 2 times negative 1, I believe that gives me positive 2, plus 2 times negative 1 gives me negative 2, and negative 9 times negative 1 gives me 9, plus 8 times negative 1 gives me negative 8. And I can see when I do the matrix multiplication, I've got 1, 0, 0, 1. Cool. So multiplying that way, I've got my identity matrix. Now, something that I do have to check here, I have to actually do this both directions. If you remember from the last section, we did find out that matrix multiplication is not commutative, so you have to check the other way. 4, negative 1, 9 halves, negative 1, times negative 2, 2, negative 9, 8, and just multiplying these together, 4 times negative 2, negative 8, plus negative 9 times, negative 1 times negative 9 gives me 9. 9 halves times negative 2 gives me negative 9. Negative 1 times negative 9 plus 9. First row, second column. 4 times 2 gives me 8. Negative 1 times 8 gives me minus 8. 9 halves times 2 gives me 9. Negative 8 times 1 gives me minus 8. And I can see both directions. I've got 1, 0, 0, 1. So what you need to be aware of is, in order to verify that two matrices are inverses of each other, multiply both directions. On that part of the homework, you might be tempted to just find the identity matrix and say, it's good. Don't do that. Actually do the multiplication to show that it comes out to be the same, the identity matrix, either way. Yeah, work. You'll notice when you download my PDFs, I have all of the work there for you. Okay, so back to that vocab that we had from earlier. If a matrix is, it can be inverted, we call it invertible, able to be inverted, or non-singular. So if a matrix cannot be inverted, it is called non-invertible, or singular. I know, prefixes, they're hard, right? All right, now let's go for a couple of different strategies for finding the inverse of a matrix. I will tell you right now that there are 3, 4-ish strategies that I'm going to tell you or show you today. You get to decide which one is the best for you. So the first method is using just some multiplication here. I know that there's some matrix out there, or I hope there's some matrix out there. Let's just call it the matrix A, B, C, D. It has to be the same size as this matrix, and okay, it is square, so it's possible that it's invertible. But if I take this matrix and multiply by what I'm hoping is the inverse matrix, I should get the identity matrix. Now what I can do some quick multiplication to figure out some equations here. Like here, I've got 1 times A, or A, 4 times C, plus 4C. That would have to be the first entry in the product matrix. So A plus 4C has to equal 1. And if I go second row by first column, I'm going to have negative 1 times A, negative 3 times C, minus 3C is equal to second row first column, 0. Hey, look at that. It comes out to be a system. And even that, it's not a very hard system to solve. But we'll get back to solving the system here after we set up, well, the other multiplication. First row by second column would give me 1 times B, 4 times D, plus 4D. You guys know my handwriting is awesome. First row by second column, that would be first row and second column, has to be equal to 0. Second row by second column, negative 1 times B gives me negative B. Negative 3 times D gives me minus 3D is equal to second row, second column, 1. Okay, cool. Look, I've got two systems. Solving those two systems allows me to get, opposite coefficients here. So opposite coefficients, I can just add down the columns and eliminate. A and negative A, that cancels out. 4C and negative 3C gives me C equals 1. Over here, well, actually, let's finish this up first. I could use the first equation, and I can have A plus 4C is equal to 1. Subtract 4 from both sides, and I've got A equals negative 3. Hey, look at that. I know this is negative 3. I know this is 1. Yeah, there's my first entries into my inverse matrix. Oh, elimination works exactly the same. Look at that. The coefficients of these two systems are identical here. So add down, I've got D equals 1. Nice. I've got B plus 4 times D is equal to 0. Subtract 4, I've got B equals negative 4. Hey, cool. And now all that's left here is to write down my answer. A inverse is equal to, okay, I see up here, I've got it in the format A, B, C, D, and nothing else. A was negative 3, B is negative 4, C is 1, and D is 1. Hey, cool, there's my identity matrix. And if you want to, you can actually go in and do the multiplication, see if when you multiply A times A inverse, you get the identity matrix, and then do the reverse, just like what I just showed you there. I do want to show you when I did this before on the answer key. Instead of using A, B, C, D, I just used X11, X12, X21, just the location in the matrix, and laying it out where the matrix multiplication ends up being equal to the identity matrix. So a little bit more, I don't know, it's just kind of a little bit more confusing doing with the X11 and all that stuff. But what we do have to identify, just like I showed you before, I did use the A, B, C, D, but what you have to really focus on is the coefficients of these systems are identical to each other. The only thing that is different is we've got the 1, 0, 0, 1. So this allows us to introduce something called a doubly augmented matrix. Down here again, doubly augmented. A doubly augmented matrix, you take the original matrix, put it on the left side, do these vertical ellipses, put the identity matrix on the other side. This allows us to stay a little bit more organized as far as what we're going to do. If you like the system method for like beginners, that's generally an easier entry point for this, but using the doubly augmented matrix is a little bit more efficient. It allows us to do things. What we're really trying to do here is we're trying to change this side into the identity matrix. So we want to change 1, 0, 0, 1 just by doing the elementary row operations. What the easiest way to do for this is to get it in the format of just numbers along what we call the main diagonal, and then a 0 right here, and then go through and divide and then add down the columns. So just looking here, I can see if I take row 1 and row 2 and add them together, I'm going to get 0 in that first column. I'm going to keep R1 the same, using that same notation that I showed you guys a couple of sections ago. So real quick, just copy down the first row. Second row now is going to be R1 plus R2. 1 plus negative 1, 0. 4 and negative 3, 1. 1 and 0, 1. 0 and 1, 1. So you can actually see the second row of the left-hand side here is now the identity. All that I have to do here is go and do some other elimination to get that to be 0. And what I do there is row 1 is going to be, let's see, I could do row 1 minus 4 times row 2 and keep row 2 exactly the same. And now I can actually see here, row 1 would be 1 minus 4 times 0, so 1. 4 minus 1 times 4 would give me 0, dot, dot, dot. 1 minus 4 times 1 gives me negative 3. 0 minus 4 times 1 gives me negative 4. And second row stays the same. Now I will note that this is the exact same matrix that we just inverted in the other method. You should recognize right over here, we now have the inverse matrix. So A inverse is equal to negative 3, negative 4, 1, 1. Not that anybody asked, but this is my favorite method for finding an inverse matrix, just because I find it a little bit easier to keep it organized, which again, I think I've tried to stress in this unit. Organization is key. You can see, it's all the same stuff over there. If you're interested in seeing the algorithm for it, it is laid out in the PDF. I'm not going to bore you with that too much. It's basically what we just went through. If you want more time to write this down, just pause the video. And now we're moving on. You can see here's the 2 problems that I have for you guys to try. Again, pause the video, try it with either method using either the systems or the doubly augmented matrix. Pause. And then we're picking back up. You can see I used the doubly augmented matrix on this one. The number 1 was almost in identity format. So this is where you want to get just like numbers along the main diagonal, and then you can just divide to get the inverse matrix, and the inverse matrix here would be 1/2, 0, 0, 1/3. Over on this side, it looks like what I tried to do was get 0 here, then get 0 here, and then I can just do the division to get my inverse matrix of negative 1/4, 1/4, 3/2, negative 1/2. Again, do you have to know either of those methods? Not necessarily, because I did all this math for you. All this math leads to, well, you can't tell on this right here, but the highlighted portions are the important part. Actually, let me type it up real quick. There we go. Typed it up, and you can actually see I've got a formula right here. If the matrix A is the 2x2 matrix given by A equals A, B, C, D, A inverse, A is invertible if and only if AD minus BC equals 0. If AD minus BC is not equal to 0, the inverse is given by A inverse equals 1 over AD minus BC times the matrix D, negative B, negative C, A. It's very important to keep track of where A, B, C, and D are. Now this looks like a whole bunch of difficult stuff to do, but it's really not. So just to point out, I am now going to do number 2 right here using that formula. Again, we did number 2 already. We have the answer. But if I've got negative 2, 1, negative 6, 1, I can find the inverse by doing 1 over AD minus BC. Now, again, you could memorize where A, B, C, and D are, but what I find easier here is AD is just the main diagonal. You multiply along the main diagonal, negative 2 times 1, minus BC is just along what we call the secondary diagonal. So 1 times negative 6. Again, you could memorize the locations and use that, but I just like to have a feel for it. And then multiply by D, negative B, negative C, A. What I look on here is on the main diagonal, I just flip the locations here. So I'm going to take that 1 and put it in the upper left. Take that negative 2, put it in the lower right. And then along the secondary diagonal, B and C stay in the same location. They're just negated. So negative 1 and positive 6. Yeah. Now looking a little bit further here, I've got 1 over negative 2 minus negative 6. So 1/4 times 1, negative 1, 6, negative 2. Distributing in that 1/4. Well, not distributing, but doing the scalar multiple here. I've got 1/4, negative 1/4, 6/4, which bothers me. I'm going to clean that up here in just a second, and negative 2/4. Again, these two bother me just in that they're not simplified. So I've got 1/4, negative 1/4, 3/2, negative 1/2. And you can see I actually have, darn it, it appears that I have a mistake over here, because I know this is supposed to be negative 1/4 and that's supposed to be positive 1/4. Looking right up here, when I had negative 4, I should have divided by negative 4 here. So this would be positive, this would be negative. All right. But you can see, I get that just by using the formula. So if you like using this formula, you can use the formula from here on out. Just point out we've got another problem right here. I'll pause for like a minute or two. Well, not really a minute or two, like a second or two. We can actually see here to find A inverse. Again, that's A. A inverse, oopsies, forgot about the fraction. 1 over, multiply along the main diagonal, 6 minus negative 2 times negative 1 gives me 2. Times, flip along the main diagonal, 2, 3. Negate along the secondary. 1, 2. Do 6 minus 2, I get 1/4. 2, 1, 2, 3. Multiply by the scalar, I've got 1/4 times 2. I'm going to cut some steps here. 1/2, 1/4 times 1, 1/4. 1/4 times 2, 1/2. 1/4 times 3, 3/4. Woo! See, it can be that simple. By the way, I don't care which method you use. If you like using the formula, use the formula for the entire assignment that I'm going to give to you guys. Singularity. To find the inverse of this matrix, we would have to have 1 over negative 2 times negative 9. I believe that's 18. Minus negative 2 times negative 9. That's still 18. Negative 2, negative 9, 9, 2 is equal to 1 over 18 minus 18. Count on your fingers. 0? What the heck? You're not allowed to divide by 0, right? Well, if we remember back to the formula actually said if AD minus BC not equal to 0. If AD minus BC is equal to 0, you end up dividing by 0. This matrix does not have an inverse. It is singular or non-invertible. It looks like I had the same exact amount of snark when I made this flip chart before. Okay, cool. Don't pay attention to this part. This matrix right here. To find that inverse matrix, super difficult. Not really. I can just use my calculator here. You can actually see I've done an inverse matrix on this calculator recently. In order to do that, go into your matrix menu. That's second X inverse right here. Go over to edit. Put in a 3x3 matrix. So change it to 3x3 if it's not there already. And then just start typing in numbers. Whoopsies. Negative 2, 1, negative 1, 0, 0, negative 1, 4. Boom! Alright, cool. Exit out of here, go to the home screen. Make your screen say a inverse by going to the matrix menu again, select the name that you edited previously, and then hit the inverse button, and then hit enter. Hey, look at that. There's my inverse matrix. I think I told you guys that your calculator will actually convert the entire matrix into fractions, so that I can see, because again, fractions just look so much cooler than decimals. If you don't believe me, you are wrong. There we go. I will tell you that the only matrices that you have to invert by hand on the test are going to be 2x2 matrices. And one last little bit of trivia is this thing right here. In order to solve, it's another strategy for solving systems of equations. So I'm just going to show you how that would work if you are interested. And I really, really do hope you are interested. So looking over here, we actually have, if I take the coefficients of this matrix, 1, -2, 2, -3, and multiply by x, y, I would have x times 1, 1x, -2 times y, -2y, so I would have x minus 2y equals 3. Second row, I would have 2x minus 3y equals 4. So the first step in solving a system using this method is to set that up. Next thing, invert this matrix right over here. So I'm just going to do some scratch work. 1 over -3 times 1, -3 minus 2 times -2, -4 times the matrix flip along the main diagonal, -3, 1, negate along the secondary diagonal, 3 minus -4. Oh, that's just 1. So the inverse matrix is just -3, 2, -2, 1. Now I know if I take this matrix and just kind of like insert it right here, -3, 2, -2, 1, and multiply it by this matrix because of the property of inverse matrices, that's going to give me the identity matrix. Since I multiplied on the left over here, I actually have to multiply on the left over here. Remember, matrix multiplication is not commutative, so where you put it is important. Again, just doing some quick math here. -3 plus 4, 1. 6 minus 6, 0. -2 plus 2, 0. 4 minus 3, 1, times x, y is equal to, let's see, -3 times 3 gives me -9 plus 2 times 4, 8. -2 times 3, -6 plus 4. Property of identity matrix, left-hand side is just x, y. Right-hand side, -9 plus 8, -1, -2. I now have an alternative way of solving a system of equations, which really that's the whole crux of this unit, is solving systems of equations. And ladies and gentlemen, there's your assignment. It's posted on my website as well, so you can get it there. But hey, this was fun. Let's do this again sometime. I guess since this is on YouTube, I have to say, don't forget to smash that like button down there. And yeah,